We now discuss the solution of a problem from the section Real Analysis. The problem is related to a property of connected metric spaces. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and it is a multiple choice question and it is from the part B. The given question is, let X be a connected metric space with at least 2 points. Which of the following is necessarily true? We are given 4 options. Option 1, X has finitely many points. Option 2, X has countably many points. Option 3, X has uncountably many points. Option 4, no such X exists. So we are given X to be a connected metric space with at least 2 points. Then what is necessarily X be? That means here the four properties are given, and X is necessarily has one of the properties, and we have to find out that property. Agreed. That's our given question. Let's now discuss the solution of the problem in detail. We recall the following result. The result is a connected metric space having more than 1 point is uncountable. A connected metric space having more than 1 point is uncountable. Then out of these 4 options, option 3 is true. Then the answer is option 3. So that closes the discussion of the solution of this. If you know this result, then option 3 is your answer, and you get the full marks for this one. And now what I will do is, the following is an alternate argument normally the students will be doing to arrive at the answer. What is the argument? The argument is we take a known connected metric space with at least 2 points, and we recall the set of real numbers under the usual metric D is a connected metric space with at least 2 points. We have the metric space X, D, where X is the set of real numbers and D is the usual metric. It is well known that RD is a connected metric space having uncountably many points. So in this example, it has uncountably many, and if X is a connected metric space with at least 2 points, then which of them is necessarily true? That means if X is a connected metric space with at least 2 points, then one of them must be true. Necessarily true. So that means here by this example, the X has uncountably many points is the correct option. Options 1, X has finitely many points is not true, because R has uncountably many points, and so also 2, X has countably many points is not true, and option 4, no such X exists. So here is a X is equal to R comma D exists. So therefore, options 1, 2, 4 are not true and option 3 is true. So that is the solution and its discussion. And now I will prove the above result, this result, that is a connected metric space having more than one point is uncountable. I will prove it in the next slide. So that is the result. The result is a connected metric space having more than one point is uncountable. Now, I will now give you the proof of that one. Proof. Let capital X comma D be a connected metric space having more than one point. So, having more than one point means there will be at least 2 points. Let A and B be two distinct points of X. That means A not equal to B. And the distance between A to B, we take it as R. Let R is equal to the distance between A to B. A not equal to B, therefore R is not equal to 0. Agreed. Agreed. Now let T belongs to the open interval 0, 1 and U suffix T, UT is, we define it as the set of all X belongs to X such that the distance between A to X is less than T times R, where T belongs to 0 to 1 and R is the distance between A to B. So UT consists of all those elements of capital X such that the distance between A to X is less than TR. And we define VT as the set of all those elements X belongs to X such that the distance between A to X is greater than T times R. T belongs to the open interval 0 to 1 and R is the distance between A to B. Agreed. Now, UT and VT are non-empty. The reason is A belongs to UT. So, if you say A belongs to UT, how? The distance between A to A is 0, 0 less than TR. T belongs to 0 to 1, which is positive, R is positive. So, 0 less than TR is true. Therefore, A belongs to UT and B belongs to VT. Why? The distance between A to B, must be greater than TR. What is the distance between A to B? R. R is greater than T times R. Why? Because T lies between 0 and 1. So T times R will be, say R is greater than T times R. T times R is certainly less than R. That is R greater than TR. Therefore, B belongs to VT. So UT and VT are non-empty and clearly there is nothing common between UT and VT. Why? Because all those elements of X, which satisfies the distance between A to X is less than TR, there it is greater than TR, therefore no element will be common between them, and UT, VT are open sets. So now we have a disjoint open sets are there, non-empty disjoint open sets are there. Suppose I say UT union VT is equal to X. Then X will be disconnected. Why? Because you have a separated sets here. UT intersection VT is empty, UT VT are open, they are non-empty. And if you say the union UT union VT is X, then this UT VT are separated sets for that, and thereby capital X becomes disconnected, which is a contradiction because capital X is given to be a connected metric space. So that's not possible. So now X is not equal to UT union VT because capital X is connected. Right. So by seeing UTVT definitions, there will be, therefore there exists an element xt belongs to capital X such that the distance between A to xt is exactly equal to TR. Right, correct. So this is X not equal to UT in VT. That means there will be some elements in X which are not covered under UT and VT. Therefore, there exists a xt corresponding to that t belongs to 0 to 1. There is an element that belongs to X such that the distance between A to X is equal to TR. Correct. Now, what I will do is I conclude that for each t belongs to 0 to 1, there exists an element xt belongs to capital X such that the distance between A to xt is equal to t times R. Now collect all such xt's corresponding to every t. Collect all such xt's and name that set as capital A. Let capital A is equal to set of all those xt belongs to capital X such that the distance between A to xt is equal to TR, where for each t belongs to 0 to 1. So we continue our discussion in the next slide. So we have that A. A is the set of all those xt belongs to capital X such that the distance between A to xt is equal to t times R, where t belongs to 0 to 1. So now clearly A is a subset of X. A is a subset of X. Agreed. Now our claim is this set A is uncountable. If I prove this capital A is uncountable and A is contained in X, A is uncountable, then X will be uncountable. Thereby our theorem will be proved. Right. Now we define a function f from the open interval 0 to 1 to capital A. It's a function. We define it as for each t there exists a xt belongs to capital X such that the distance between A to xt is t times R. We know. So for each t belongs to the open interval 0 to 1, there is a xt. So we will define our function to be f of t is equal to xt. Now I will show you that it is a one-to-one mapping. That means this function is injective, I want to show. So let us take t1, t2 belongs to 0 to 1 with two different elements of the open interval and t1 not equal to t2. t1 and t2 are distinct. This implies corresponding to t1, t2 there exists xt1, xt2 belongs to A such that the distance between A to xt1 is t1r and the distance between A to xt2 is equal to t2 times R. So because they belong to capital A, this is true. Now this will imply the distance between A to x times t1 is equal to t1 times R, and t1 not equal to t2, it is not equal to t2r, where t2r is the distance between A to xt2. This is true because t1 not equal to t2. Thus we have the distance between A to xt1 is not equal to the distance between A to xt2. That will imply xt1 is not equal to xt2. So xt1 is not equal to xt2 will imply f of t1 is not equal to f of t2. So thus I have proved t1 not equal to t2 implies f of t1 is not equal to f of t2, and thereby this function f is injective. So thus f is injective. Right. So therefore now f of 0 comma 1, f of the open interval 0 to 1, that is the image of the open interval 0 to 1 under the map f, and that will be, let us say, capital B, and that will be an infinite subset of A because the open interval 0 to 1 is an infinite and f is injective. Therefore B is an infinite subset of A. Agreed. Now we restrict our function f open interval 0 to 1 to capital B, which is a subset of A, and capital B is the image of 0 to 1, and f is already injective, and it will be onto also, because it is equal. Because f of 0 1 is exactly equal to B, so it is onto also, it is surjective also, and thereby it is bijective. When it is bijective, they will have the same cardinality. That means the cardinality of the open interval 0 to 1 is equal to the cardinality of B. That means the cardinality of B is equal to the cardinality of the open interval 0 to 1. The open interval 0 to 1 cardinality is the continuum C. That is, the set 0 to the open interval 0 to 1 is uncountable. Therefore, its cardinality is C. That is continuum. Therefore, cardinality of B is equal to C, which implies B is uncountable. Now, what is B? B is a subset of A. B is a infinite subset of A. And now B is uncountable. So, B is contained in A. B is uncountable. Therefore, A is uncountable. A is uncountable. Now, we have already seen A is a subset of X. Now, A I have proved to be uncountable. Therefore, capital X is also uncountable. Therefore, capital X is uncountable since A is contained in X and A is countable. Therefore, capital X is also uncountable. So, that's what precisely we wanted to prove. So, hence the result. So, there's a connected metric space having more than one element is uncountable. That's the result what we have proved. And with this, the discussion of the solution of that given problem on the connected metric spaces is completed, and I am sure that you have understood the solution of this problem and the proof of the result what I have mentioned there. I wish you all the best. Thank you.